our wonderful chief guest of the day, Jayant, Murthy, senior professor from Indian Institute of Astrophysics. A warm welcome to you. Thank you for accepting lecture for us. And I would like to give a welcome speech about our chief guest also. So in this, our chief guest of the day, Jayant Murthy, Professor Jayant Murthy, has done a research, has worked as a research scientist in Johns Hopkins University in the Department of Physics as well as Astronomy, and he has worked in National Research Council Fellowship, NASA, and he has done his PhD in Johns Hopkins University. So his area of interest: space missions, interstellar dust, and diffuse radiation field. So he has working many projects. One of the project was Galaxy diffuse data and hardware development for high altitude balloons and low altitude space payloads. From that, he has done various presentations. Even in TEDx, he has given a speak. And also he's a professional member in International Astronomical Union. So it is one of the worldwide recognized organization, International Astronomy, and American Astronomical Society. Also, he is a professional member over there, as well as he is a professional Astronomical Society of India. So thank you, sir. Thank you for accepting the invitation, and I request you to give your presentation on the topic of space astronomy.
Okay, thank you very much for asking me. I must say this whole online presentations are new to me. I think it's an excellent idea in that it means I don't have to travel. I can sit at home and give talks. The disadvantage, of course, is that I can't tell if anyone is sleeping in the audience. So I'll just continue on. So what I'm going to be talking about is space astronomy. And in order to do that, I wanted to start with a little bit of history, meaning the people who really started the field, started space astronomy. And so there were, of course, from time immemorial, there have been people who have talked about going into space. And this was from, there's a little noise in the background. I think that's, okay, great. So that is from people like Kepler, who wrote about the men in the moon, Jules Verne, who had his famous from the Earth to the Moon, where he had a 3-mile-long cannon in Florida, where he shot astronauts, or as he called them, Selenonauts, to the moon. They went there, they met the moon, and somehow they came back. But these are all stories. And so the people who first put the field on a scientific footing, the first of these was Tsiolkovsky in the Soviet Union, or as it then was in Russia. And what he did was he derived the basic equations of space travel, the equations of rocket dynamics, how you go into space, and so on. Followed by the experimentalists, by the rocket people. One of them was Robert Goddard. You may know of Robert Goddard from the Goddard Space Flight Center in NASA, where I was for I guess almost 3 years. And what Goddard did was he liquid fuel rockets. Now these are rockets that don't have solid fuel, but rather have liquid fuel. And he had a whole program of experimentation. He would go to fields in, I think he was at the University of New Hampshire. So he would go to fields and he would launch these rockets. Now, he was a very quiet man. He didn't like the press, and the press didn't like him either. So the New York Times in 1920 said that his rockets are really stupid because they'll never work outside an atmosphere. What they meant is that outside an atmosphere, the rockets won't be able to push against the air. Now, this, of course, is not the way rockets work. And in 1969, after Apollo 11 had set off to the moon, the New York Times published an apology, and they said that further investigation and experimentation have confirmed the findings of Isaac Newton in the 17th century, that is, Newton's third law, and it's now definitely established that a rocket can function in a vacuum as well as in an atmosphere. And the way a rocket works is not that it pushes against the air. What it actually does is that it is, as said, Newton's third law. There's a lot of hot gas the fuel inside the rocket is ignited. Once it's ignited, it explodes. The hot gas goes out the back end. And in order to conserve momentum, Newton's third law, the rocket goes forward fast. So regardless of whether there's an atmosphere or not, the rocket will work just because of this conservation of momentum. Now, it took the Times about 50 years to apologize. This is much faster than it took the Catholic Church to apologize for the hounding of Galileo. That was about 450 years. Now, on the German side, there was Wernher von Braun. And this was what he did was he started up the German V2 rocket program. He headed the V2 rocket program. And what the V2 rockets were rockets that were intended to bomb London. This was in the middle of World War II. And the rockets were launched from Peenemünde, the rocket site, and they went and hit London. The Germans were already losing the war. It was clear that they were losing the war. And so they thought that as a final push, they'll try this and hope that the English are so terrified by the rockets that they'll surrender. Now, after the war, when the Allies were just about ready to overcome Peenemünde, or to take over Peenemünde, the Germans sent an SS death squad over to assassinate von Braun and his entire team, because they said, well, now that we've lost, we don't want anyone else to get the benefit of the work we did. And so von Braun and his team, they found out about this, and they escaped in the middle of the night. They went through some farms, they climbed over cows and whatnot, and eventually gave themselves up to an American entry squad. The Americans took them and a number of captured rockets to the US, and they put them in Huntsville, Alabama, at what is now the Marshall Space Flight Center. And they told them that you can work on whatever you want, but stay here, don't come on the news, just stay hidden, and just go ahead and keep working. Because of course the war had just been over, and they didn't want these Germans to come on TV. They had just beaten the Germans in a very difficult war, and they didn't want them to be the face of their rocket program. On the Russian side was Sergei Korolev, and he was called the Great Designer. He actually had a very hard life because he was caught up in Stalin's great purges. And so Stalin had sent him to Siberia. He was in a gulag there. He was not brought back until the middle of the war, middle of World War II. And then by that time, his wife had left him. His health had been ruined. And anyway, he took over the Soviet missile program, or the Soviet rocket program. And so he was responsible for all the Soviet achievements, just starting with Sputnik, going on through Yuri Gagarin, Valentina Tereshkova, and so on. At the time, he was only known as the Great Designer, because the Russians were afraid that the CIA would try to assassinate him. And so they never published his name. They only called him the Great Designer. It was not until the breakup of the Soviet Union and the declassification of all the documents through the Soviet era that people really understood how much Korolev had done. On the other side, von Braun, who was one of the major people in NASA, he was heading much of the NASA space program. it was becoming increasingly clear that he actually had known about much of the abuses in the German rocket program. At Peenemünde, they used Jewish slave labor to dig a lot of the tunnels. And von Braun had always denied his knowledge. But in retrospect, it does appear that he did know about it. And he went along with the Nazi torture. Now, the space era began with Sputnik, October 4th, 1957. And this was Sputnik. It was a football-sized object, and all it did was it beeped. Anyone with a ham radio could listen to it. And as Sputnik went over, ham radio enthusiasts all over the world, they just heard it beeping. All it did, it just beeped. But what was it doing when it was beeping? It was saying that we are better. Remember that this was the time of the Cold War. It was 12 years after World War II. The common victory over the Germans had been forgotten. Now you had the Soviet bloc and American bloc, who were in a competition for power over the entire world. And what Sputnik did was it said that we in the Soviet bloc are better than you are. We put something up into space that you can't do. Now, in the middle of the Cold War, this was a time when people were scared of atomic war. In the 50s, in the 60s, until the fall of the Soviet Union, there was always this fear that the atomic war would break out. And this was one of the classic movies put out by the American, the Atomic Energy Agency, and it's well worth watching just for a laugh. It's on YouTube, and it's called Duck and Cover. And this guy over here is called Bert the Turtle, and what he says is that anytime you're in danger of a nuclear attack, you duck and you cover. What this meant for school children who were sitting in schools, they had these old-fashioned desks where the chair was attached to the desk. You were supposed to duck under your desk. If you were not in school, you were supposed to duck into a hallway, or you could cover yourself with a newspaper. Throughout my time at Johns Hopkins, every Monday at 1 o'clock in the afternoon, they had the air raid siren. And in that air raid siren, you were supposed to go down to the basement and make sure that you could stay safe. They had bomb-proof doors down there. So this was, and Apollo meant, what Sputnik meant was that if you can fire a satellite that goes around the world, then you can fire a missile. It's not just a satellite. It's not just a ball that's around the world. You could launch a nuclear bomb, and if you launch a nuclear bomb that goes all around the world, well, you can stop it in Colorado or New York or Los Angeles or wherever you want. And so what this did was it caused a worldwide interest in science. Remember that World War II had in many ways been the physicists' war. There was the most prominent example, which was the nuclear bomb. But in addition, there was radar, there was LIDAR, all of these other things. Immediately after the war, a lot of effort was put into science. And this is where the American lead science really came from the investment that was put in after World War II. Now, by 1957, all of that had been forgotten. And was going away from science and going away from physics. But once the Russians launched Sputnik, now suddenly a lot of money came into science, and more particularly into space science. So there's stories of people sitting in their offices and black suits and black sunglasses coming into their office and putting a desk with them and putting a briefcase with $1 million on their desk and telling them, hey, start a space program. So a lot of money went into space research at the time. Now, the Americans tried to match the Russian launch. And so I'll just be quiet for 30 seconds and let you watch this. This was a Vanguard 1 program.
A series of space experiments that yielded valuable data to the world's store of scientific knowledge. There were a number of failures during the year, and the United States promptly announced them. The first and most spectacular of these was Vanguard at the end of 1959. All Vanguard failures all achieved takeoff, but trouble occurred either in the second or third.
You saw what happened. So the press had a field day with this. The Vanguard program, which was done by the Navy, tried to launch several satellites, and they had spectacular failures, like that one which rockets are supposed to go up. This one went down instead, and the press had a field day. They called them things like Flopnik or No Goodnik, after Sputnik, of course. And finally, the Americans told von Braun, who was, if you remember it, in Huntsville, Alabama, he said, okay, you guys can go ahead and launch a rocket. And so the first American satellite was Explorer 1, which was launched in January of 1958. Now note the short time gap here. Sputnik was October 1957. Explorer 1 was January 1958, after already 3 failures. We couldn't imagine of anything being done so fast now. Now, for whatever reason, all space missions seem to take years or decades even. But those were the early days, and in those early days, things happened fast. Now, even on Explorer 1, there was already a space experiment. And what it was a Geiger counter. And as the Geiger counter went up, it detected belts of increased radiation. Now, the person who was responsible for the Geiger counter was, at the time, a young postdoc called James Van Allen. And so those belts of radiation are now called the Van Allen belts, after James Van Allen. He died fairly recently. He was working at the University of Iowa, and he continued to work there until well into his 90s. Now, so you had Sputnik, then you had Explorer, then after that you had all of the Russian successes. Yuri Gagarin was the first man in space. Laika was the first dog in space. Valentina Tereshkova was the first woman in space. And so the Americans said, okay, now what can we do? Beat the Russians. The Russians are beating us into space. They're doing everything first. What can we do that's important and where we will be first? And so in 1961, Kennedy, before the Houses of Congress, he made a long speech which had many things in it. And he said, we will send a man to the moon and bring him back. I'd like to highlight here that he said a man to the moon and bring him back. And this was deliberate. This was in the 60s, and this was a very era. At the time, the space program was men, and not only, it was all white men who, all American men or all Russian men. They were all, it was a very segregated time. And now, of course, we know that there were many women involved, including many Black women. If you ever get a chance to watch the movie Hidden Figures, it's an excellent movie, but with Katherine Johnson. But the people in the front were all white men. I'm a little disappointed in the Indian astronaut program. It's a very exciting program, but I'm disappointed that they've restricted it to men only. In 2020, there should have been no question that there are women qualified to fly, and it would have made a significant statement if, in fact, our first astronaut was a woman. But be that as it may, the Apollo program started in 1961, and by 1968, they had gone around the moon. So this was Apollo 8, and the three astronauts, Anders Borman and Jim Lovell, who was later commander of Apollo 13, were the Time Men of the Year. They took this famous picture from the moon, and this is called Earthrise. As they came around the far side of the moon, they saw the rising Earth, and this picture, in many ways, became a postcard for the environmental movement. Rachel Carson and the Silent Spring was only a few years before this, and from this picture, it's clear that the moon, which Buzz Aldrin later called a magnificent desolation, is just there. It's not. We can't go and live on the moon. We can't live on Mars. There's no place for us other than the Earth. Here, it's called the Big Blue Marble. Carl Sagan later played off of this to call when he got Voyager to take a picture of the back from beyond the orbit of Jupiter, the little blue marble. So when we look at all of humanity, this is all there is. We're all on this one planet. When we think of the vastness of space, we're all together. We're all human here. In 1969, Neil Armstrong landed on the moon. This picture is actually Buzz Aldrin. There are apparently no pictures of Neil Armstrong on the moon, because Buzz Aldrin only liked taking pictures of himself. So he never took a picture of Neil Armstrong. But this is Neil Armstrong on the moon. And this is actually a member from the space age. I was not born Sputnik. I just barely remember Apollo 8, but I remember Apollo 11 well. And for me, it was a big influence in probably in my going into astronomy. Now, many people ask about the moon hoax, but I never talk about it. I will just point you to this one website, badastronomy.com, where Phil Plait goes into all of the points that they supposedly make, this conspiracy theory, and he points out how each one of them is silly. Now, the reason that I don't talk about it is because there's so much good science in the world that it just doesn't make sense to learn about bad science. There's so many interesting things. Why learn about bad science? The other thing is that I have been on TV shows with astrologers, and it's always depressing because astrologers have no compunction to tell the truth. See, we're scientists, and as scientists, we're supposed to always tell the truth. We have to convey our understanding of the world. We can't lie about facts. We can't lie about theories. But these guys have no necessity of telling the truth. So they come up with stacks of paper and stacks of theories, and you just can't argue with them. They're so confident in their lies that you just cannot argue. So I try not to get on TV shows with astrologers anymore. Now, the one fact that I was interested in, and I don't think this will come through in the video, but please do look it up, is the flag looks like it's waving. And one of the Sherlock Holmes once, or Watson once told Sherlock Holmes that the Earth went around the sun. And Holmes said, now that you told me, I'm going to do my best to forget it because my mind can only hold so many things. And this just doesn't help me solve crimes. So I only remember things that interest me. I don't remember people. I don't remember names. I only remember things that actually interest me. And one of the things that interests me is why the flag looks like it's waving. And here are two different pictures of Buzz Aldrin. In the top one, I think he's saluting the flag. In the bottom one, his hand is down. And so if you blink the two photographs, you can see that everything moves. The shadows move a little, the astronaut move, but the flag looks the same. So why does the flag look like it's waving? It turns out that a spring broke. NASA had tried to extend the flag out all the way, but they couldn't. The spring broke, and so it looks like it didn't extend out all the way. So that's why the flag looks like it's waving. In all future missions, they liked that it looked, because flags should look like they wave in the wind. And so they did that deliberately in all future missions. So the Apollo program was all political. It was done because of the space race. It was to show that the Americans were better than the Russians. And so that was one of the reasons to go into space. But there's also many benefits of going into space. And so here's a picture of 4 different cyclones, coast of India. We remember that Amphan came by earlier this year and caused a lot of damage. Clearly, it's a good thing for fishermen to know. It's a good thing for people to know if a cyclone is heading their way. So weather forecasting is one of the great benefits of going into space. Weather forecasting from satellites. Another thing that people do is remote sensing. One of these buildings is my house. I won't tell you which one, but we all have phones. We call taxis. We order food. We find our way to places, and these are all possible because of GPS. So our phone, because of our phone, we know where we are at any given time. We look down on the world, and by mapping cities like this, we can see land use. Maybe we might see that this one space here has been taken over by a building. Maybe that's legal, maybe that's illegal. Well, we can check all this. If we look at farmland, we can see that the farmland has changed from this use has changed from wheat to rice, or look out for fish stocks in the sea. So this is all different uses of remote sensing. And all of this is worth money to people. So all of these are commercial uses of going into space. Military applications is very relevant now. We have these satellites that go over Ladakh, and from those satellites, we can see what's happening in the around that line of control. So these are all benefits of going into space. That's not what I talk about. What I talk about is pure astronomy. That's blue sky research. It's research that's of no particular use to anyone. And so before I can talk about astronomy, it's important for me to tell you why I think it's important that we do astronomy. And so the standard answer is that from basic science, you get advances that you would never have dreamed of. Things like X-rays, things like lasers. These came out of basic research. GPS, which I talked about earlier. GPS would not work if we did not understand the special theory and the general theory of relativity, because you have to correct for both as the satellites go around the world. And so these are all practical applications of basic science. The science that we do today has practical applications generations down. But this is only, to me, the more important reason of why we do science is simple curiosity. We do science because it's important for us to understand the world around. We do many things that have no practical use in our lives. Many of you, I hope many of you are listening to me. We go to movies. Shah Rukh Khan, by the way, is paid a lot more than I do because you go to his movies. We go to art school, we paint, we dance. So all of these things we do because we're human. And I think this is why we do science. We do science because we want to learn about our universe. For instance, there's a black hole in the center of this galaxy. And once I tell you there's a black hole, it's easy for you to understand. The black hole in the center, and everything is going around that black hole. So you can see this galaxy rotate around the black hole. So I think it is important for us to do curiosity-driven research. And I think this has a practical application also. One of the reasons that Bangalore has come to be known as the technology city of the country is because of the Indian Institute of Science and because of all the engineering colleges that grew up in Bangalore. Silicon Valley grew up because of Stanford. MIT has given rise to a number of institutes or number of industries around that. So when you have a university, it seeds a whole number of knowledge industries around it. Now, once you accept that astronomy is important, why is going to space important? Because that's what I do. I do space astronomy. Now, space astronomy is a lot different from ground-based astronomy. It's a lot more expensive because when you go up into space, you have to launch yourself, or you have to launch out in a rocket. This is the FUSE satellite going up in a Delta II rocket. You waste gas as you go up, a lot of fuel. You go up, and once you're up, there's nothing much that you can do. You only last for a few years, and there's no room for mistakes. And so why do you go out into space? Well, there's several reasons. One of the main reasons is because of sky transparency. We're down at the bottom of the atmosphere, and all we can see is the visible light from the sky. So we have colors that you see, all the colors of the rainbow. You can look up and you can see in that. So you see the sun, you see stars. If we go down to shorter wavelengths, we can't see out anymore. So in the field that I do, ultraviolet astronomy, you can't see anything from the ground because the water in the air absorbs all of the UV light. This is a good thing for us because because when we look up, or because if the ozone layer didn't absorb all the ultraviolet, we would walk around with sunburns every day. So, but the result is that when I look up from the ground, I can't see light from the sky. Similarly, as I go to longer wavelengths, there's a lot of the sky that I can't see because I can't see radio waves. I can't see microwave because the water in the air absorbs the microwaves. I can't see the very long wavelength radio waves. And so the only way to observe these parts of the spectrum is to go above the air. In the case of microwaves, it might be enough for me to go up into an airplane or maybe to a high mountain. If I want to observe the ultraviolet, I need to go above the ozone layer. So I need to go out into space. Now, the reason that I want to observe these other wavelengths is because the reason I want to observe these different wavelengths is because the wavelength is related to the temperature. As you probably know, the shortest wavelength light, the gamma rays, have the highest energy. The longest wavelength light, the radio waves, have the least energy. So you go from short wavelength, high energy, to long wavelength, low energy. And the same thing as temperature. Because if you think about the air in your room, for instance, the hotter the air is, the faster the molecules go around. 3/2 kT is equal to 1/2 mv squared. So the higher the energy, the higher the temperature. So gamma rays, the highest part, the shortest wavelength part of your electromagnetic spectrum, come from the highest energy parts of the universe. The other side, radio waves, come from the lowest energy or the coolest parts of the universe. So if we look at our own galaxy, we can look at the central disk of our galaxy. We look at the long wavelength radio waves, and what we see in radio waves are cool gas. We see gas at temperatures of maybe 20 degrees up to maybe even 100 degrees Kelvin. As we go to shorter and shorter wavelengths, when we get to the visible, what we see are stars. And we know of the sun is about 5,000 degrees. So when we look at optical light, we look at temperatures of about 5,000 degrees Kelvin. And as we go to still shorter wavelengths, now we look at temperatures of hundreds of thousands or maybe millions of degrees in temperature. So in the gamma rays, what we see are individual black hole candidates, things like Cygnus X1 or Scorpius X1, where the accretion disks, these disks of gas, are going so fast, the central black hole, that friction heats them up to millions of degrees. And what you see is gamma rays from those accretion disks. Now, because we look at this in different wavelength regions, we also see different aspects of the universe. So now when we look at the optical, we look at the central disk of the Milky Way, and we see these dark lanes that run through the Milky Way. And what these are lanes of gas and dust. So what we see here is dust that blocks the light of more distant stars. Now, because it blocks the light, it absorbs the light of those distant stars. The dust is heated up to temperatures of 100 Kelvin or so. And so it re-radiates that radiation as a black body at a temperature of 100 Kelvin in the infrared. And so the dark area in the optical, we see as a bright area in the infrared. So looking at different aspects of the electromagnetic spectrum, we can see different phases of the universe. Now, another reason to go out into space is because the sky is bright. No matter where we are on the Earth, in Bangalore, for instance, I can't see stars that are fainter than maybe 5th magnitude or 4th magnitude, maybe 100 stars in the sky. If you go out to a rural area where there's not many city lights, you won't even recognize the sky because there's so many stars out. And so here's a picture of Orion from the space station. And even from the space station, you can see the atmosphere. So here's Orion above the atmosphere, here's Orion below the atmosphere. And you can see how much darker it is above the atmosphere. So one of the reasons to go out into space, many of the important results of the Hubble Space Telescope were from optical pictures, and they were because the sky is so much darker there. Now, another reason to go out into space is shown in this picture of this galaxy, NGC 4314. Now, this small picture is from a 2.3 meter telescope on the ground at the McDonald's Observatory. And you can see that the central square is really a blur. You can't see any details at all. But when you look at that from the Space Telescope, now you see that there's this ring of star formation where new stars are being formed that are just not visible here. So when you go out into space, you avoid atmospheric twinkling. What happens is that you look at a star, and as you look out at the star, you're looking out through all of these different layers of the atmosphere. Each layer of the atmosphere has a slightly different temperature and a slightly different density. And as it keeps changing, the index of refraction, as you look over the whole line of sight, the index of refraction changes a little. And so the star looks like it changes a little bit both in position and in brightness. And because of that blurring, you can't see the same detail from the ground as you could see from space. So why do you go out into space? Because you get new wavelength regions, because the sky is much darker, and because you avoid all these effects of the Earth's atmosphere. Space research started almost immediately after World War II. The Americans captured a number of these V-2 rockets, and as early as 1946, they launched the V-2 rockets and looked at the sun. So they saw ultraviolet radiation from the sun. Then they looked at stars. They saw stars in the ultraviolet and the X-ray. They saw the interstellar medium. They saw the radiation from interstellar gas. And so all of this was done from sounding rockets. What is a sounding rocket? It's a rocket that goes up and comes back down. So it goes up to an altitude of maybe 200 kilometers, 250 kilometers. It takes, as it goes up, it spends about 15 minutes going up, 15 minutes going down, 5 minutes at the top of its orbit. So how much science do you get? You get about 5 minutes of science from a payload that's maybe 5 kg. And so there's not so much science that you can do. It's useful now for two reasons. One is for fast science. You do things that are, if a comet is coming, there's no way that you could launch a space mission. A space mission might take 20 years to launch. So you can't launch a space mission, but you might be able to launch a rocket to look at the comet. Supernova, same thing. It might take you a year to develop a rocket. You and look at something that comes new. You can look at the sun. The sun is always changing. Good to look at the sun. You can look at the Earth's atmosphere because the Earth's atmosphere is always changing. And so it's good to look down with rockets. So these are the kinds of quick science that you can do with rockets. It's also very useful to develop expertise because there's a lot of mistakes that you can make in space. And so it's good to work out your mistakes on a $1 million rocket program rather than a $100 million or even a $5 billion space program. So some are very useful for training students. And in fact, we have not a sounding rocket program, but we have a program where we do train students in building space experiments. And all of those students have now gone on to work on space experiments. So I'll spend the last 10 minutes or so talking about some of the science that has come from these missions. Unfortunately, I can't talk about all of science. Astronomy is a huge field. It takes a lifetime to learn about everything in science, even in astronomy. And no single person can know everything. But there is a world of discovery out there, and it's good to go and learn more about it. And so one of these resources is this NASA website, science.hq.nasa.gov. Now, much of the science research from space has been done through NASA missions. ESA also has a fair number. The Soviets have a few. ISRO has a few, but the bulk of the science has come from NASA. NASA has always had the science focus as part of their mission, and I think this is correct, because scientists are the ones who push the boundaries. If you just want to put a new communication satellite up, if you want to just put a new remote sensing satellite up, all you do are incremental advances on the missions before. It's only scientists who want to do fundamentally new things. And so for NASA to develop the way it has, a lot of that can be traced back to scientists who have been working on new ways to find out the fundamental truths of the universe. And so here on this website, they have a list of all the NASA missions. You can click on any of them. You can click on any of them and get an introduction to what the mission does. Another of the things that NASA realized is that they realized that many of the people who had come in with Sputnik was an exciting thing, and it brought many people into space. And so many of the engineers of NASA had come in with Sputnik. They were teenagers at Sputnik. They launched rockets like Homer Hickam, who was the hero of the book and then the movie October Sky. And they were retiring. And they were finding that not many new people were coming into science. How do they bring in the new people? Well, they thought they could do outreach. And so it became a part of every mission that they had to reach out to the public, which we India are just starting to do now. We're starting to realize that we have to show that we are relevant to the Indian public, and we have to bring people on to the science that we do. So every one of these missions has an explanation aimed at K to 12, kindergarten to 12, and beyond, where they explain their science in terms that are understandable to everyone. So do go to those websites, do go to those mission sites and learn about what they do. Most of them, you can also download the data for what astronomical data looks like. So here's the one of the most important of the NASA discoveries, and this is this particular slide won a Nobel Prize for John Mather. He what it shows is that when you look out at the universe, the spectrum of the universe is that of a black body with a temperature of 2.725 degrees Kelvin. This is, you might have heard of the 3-degree microwave background. This is the 3-degree microwave background. And what it tells you is that I won't go into what a body is, just to tell you that once you measure the black body, you've measured the temperature. And so this tells you that the universe has a temperature of 2.725 degrees Kelvin. The only way that the universe could have this temperature is through a Big Bang. So when you look at this image, you're looking at a picture of the Big Bang. Before that, people had all sorts of ideas, steady state theory and whatnot. After this, it was clear that the only viable theory for the beginning of the universe was through a Big Bang. At the time of the Big Bang, the universe was small and hot. Now, 13 billion years later, the universe is big. In order to conserve energy, it must be cold, and that temperature is 3 degrees Kelvin. The other part of that Nobel Prize came from another experiment on this satellite called Derby, where George Smoot, whom you may have seen on the Big Bang Theory, got a Nobel Prize, showing that the universe looks the same no matter where you look. Now here is the Eagle Nebula. I'm sure all of you have seen this picture. It's a truly spectacular picture from the Wide Field and Planetary Camera on the Space Telescope. And what this is clouds of gas and dust. And so what you see is the dust here. It blocks the light from more distant, from this more distant glow. And you can see stars through this cloud. Now, these stars that you see are actually hot blue stars. They don't look hot and blue, they look red. And the reason they look red is because you're looking at them through so much dust. So the sun looks red when you look at it in the horizon because of Rayleigh scattering. All the blue light is scattered out by the atmosphere. But you might have noticed that on dusty days, the sun looks even redder because the red light is scattered out by the dust. I'm sorry, the blue light is scattered out by the dust. So in the same way, the blue light from those stars is scattered out by the dust in these clouds, and all that's left is the red light. So these stars that you see as red stars are really hot blue stars. They're young stars. They're under a few million years old. And so what you're looking at here is a stellar nursery. These are where stars are being born, stellar birthplaces. Our sun was born in a similar environment about 5 billion years ago. This is another instrument on the Hubble Space Telescope. This is the Space Telescope Imaging Spectrograph. STIS. And what they did was they laid the spectrograph across the central black hole of this galaxy, M84. So what you can see is that the light from the black hole, the light from the galaxy is neither reddened nor blue shifted, neither red shifted nor blue shifted, far away from the center. As you get closer and closer to the center, suddenly the stars are blue shifted heavily. Blue shifted means they're coming towards us very fast. As you cross the central part of that galaxy, they suddenly shift from being blue shifted to red shifted. That they go there, instead of going towards us very fast, coming towards us very fast, they're now going away from us very fast. Now, because of how much they're blue shifted or red shifted, you know how fast the stars are moving. You know that they shift from going very fast towards us to very fast away from us. And they do it in this very short space. And so what we know is from Keplers Laws, which govern the motion of the planets in our solar system, we can apply Keplers Laws to this black hole, and we can say that there's a mass of several million solar masses in this black hole in the center. We know how big the black hole is because look how small a space the shift occurs. There's so much mass in such a little space. The only way we can have so much mass in such a little space is if there's a black hole. So normally you say you can't see black holes. Here, you're actually seeing a black hole. Another way to look at a black hole is through this picture where really you see what's happening in the center. This plus sign is where the central black hole in our galaxy is. And as you look at the stars that are orbiting the center of the Milky Way, you see that they start out slowly up when they're far from the black hole, and then they whip around the black hole as they get closer. This is exactly as a comet would look like coming around the sun. When it's far from the black hole, it's slow. When it comes closer to the black hole, it speeds up and it just goes fast around the center. So again, you can measure the black hole, the mass of the black hole, and you know where it is, and so you know the density, and so you can say that there's several million black holes and several million solar masses in this small volume. So it has to be a black hole. You may have heard a lot from the Gaia mission now, And this is a mission that's releasing new data right now. And what it does is it measures distances through parallaxes. So we measure distances on the Earth through radar or through trigonometry. Even in the solar system, we can measure distances directly through radar. So we know the distance to the moon very precisely because we shoot radar off, or we shoot light off and hit the moon and come back. And what Gaia does is it measures the parallax. In the same way that when you blink, your position, your finger shifts against the more distant background. If you look from both sides of the Earth's orbit, the position of nearby stars will appear to shift with respect to the more distant stars. And this is a way of directly measuring the distance to those stars. Now, when we look out further and further, we have no way of measuring directly the distance to the furthest objects. When we have a supernova at the edge of the universe, we can't measure its distance directly. We have to use secondary measures. And these secondary measures all depend on these direct measures. So what Gaia has done is it has put the first levels of this steps on the distance scale, of the distance ladder, on a much more secure foundation. And so now we know the distances to objects within a few thousand parsecs of the sun. Another mission that has not yet come, but they're thinking of doing, is LISA. I'll just go through the last couple of slides quickly. LISA is, you know about LIGO. What LIGO did was it measured gravitational waves coming from black holes that collided. On the Earth, you're always limited because you have a lot of noise on the Earth. You have seismic quakes, you have North Korean explosions. So all of these gives you a background. And you can't do very far. So LIGO is a distance of maybe 4 kilometers. But what LISA does is it measures gravitational waves through having spacecraft in space. These spacecraft are separated by thousands of kilometers, and you measure the distances very closely, very carefully through interferometry. As a gravitational wave goes by, the distances change, and so now you can measure gravitational waves from many different classes of objects. In many ways, LIGO has opened up this new branch of astronomy. Before, we've always had electromagnetic waves. LIGO has opened up this new branch based on gravitational waves. LISA would now expand that completely new area into a new area of astronomy. A couple of other things. Global Surveyor, this is looking at Mars. You all know that there's water on Mars in the past because of these erosion channels on these cliffs. But this is a picture of the same area taken from the Global Surveyor, 6 years apart. And now there's this new shiny patch here that's water ice. So here is evidence of water, not hundreds of millions of years ago, but right now on Mars. When I was a graduate student, we had no planets were discovered. The first planet was discovered just as I was finishing up my PhD. Now, because of Kepler, there are now thousands of planets known. When I was a graduate student, we thought our system was typical. We thought that we had a solar system with rocky planets near the sun and gas giants far away from the sun. Now we know that there's all sorts of solar systems. There's planets like Tatooine, where a planet with 2 suns. There's a planet with 5 suns. There's Jupiters that orbit closer to the sun, or closer to their sun, than Mercury does to our sun. And these have all come through Kepler. And what Kepler did is like the Murthy transit of a few years ago, or like the annular eclipse of a week ago, they observe transits of the planets and of moons around their star. And I'll just flash the next slide quickly because it won't come up in the broadcast. But do look up Kepler orrery, and you get a feeling for the large number of planets and the large variety of planets that are possible through this new method. Okay, so that was called Kepler, and do look it up. So let me finish with one of the great benefits of space astronomy. Now, before the space age, astronomy was done by people going to telescopes. So they looked at the telescope through the sky and they took photographs, and then they put the photographs in their desk, and no one else would ever see their photograph. But once people started launching satellites, now a satellite is expensive, and once you satellite, you can't launch a new satellite every day. So the idea grew up that that data should not belong to one person. After all, the satellite was not paid for by the astronomer, but was rather paid for by the public. So the data should belong to all scientists, and even more broadly to the entire public. Now, in recent years, this has come along with the computer revolution, where computers are getting faster. So I do much of my research not on a big computer in my office, but rather on my laptop at home. Internet access is getting faster. We're only able to do these presentations because many of us have good computer access. Unfortunately, not everyone, but many of us have good network access at home. And now scientific results are publicly accessible. In astronomy in particular, we publish all of our results on papers that anyone can read. They're not behind a paywall that only people at institutions can read. Rather, they're open. Anyone can look at our papers. And so we've now reached a point where astronomy can be done. In an extreme, it can be done at home, but certainly astronomy can be made part of the curriculum in most colleges and universities. And I hope this is where we move into the future. So let me end here. And I don't know, do you have questions? Is there a way to ask questions?
Yes, sir. Thank you, sir. Thank you for a wonderful presentation. And I request the participants, those who are watching in YouTube, to ask their questions in the chat box itself, so that I can convey to the sir. Yes, sir. Sir, first question is, might be a question where every human being is having. Why Americans are not replying about the question on man on moon? There was an issue, like.
What about man on the moon?
Yes.
No, what about it? Why are the Americans not
replying about the question? One student has asked like that.
No, I don't know what that means.
No, actually, there is a contract with the Apollo law. There is a contract with this statement is there, that they didn't land there. So
hey, that's put out by conspiracy theorists. And unfortunately, we know about conspiracy theorists. All sorts of people who don't believe in science. And I would encourage a student to do a proper search. You can go and look at the Apollo tapes. You can look at a site like I showed, the badastronomy.com.
Okay.
And anything on the conspiracy theory is shown there. Because this is actually harmful in that there's no way to reply to people, because they believe things and you can't argue with belief. It's like arguing with astrologers. Say that Mars has no effect on my life. It's silly.
Yes.
But no matter what I say, they won't believe me. So if you say, I mean, look at look at books, read Buzz Aldrin books.
Okay.
So research.
Okay. Nice, sir. And Suman has asked that a photon or a light ray go in and come back from the.
No, the whole point of a black hole, it's called a black hole because nothing can escape the black hole. So if the escape velocity from a black hole is greater than the speed of light, the force of gravity is so strong that nothing can escape a black hole. So nothing can go in and come back out. What she may be asking about is the so-called Hawking radiation, where a black hole emits radiation. Now, the way this works is that energy is equal to mc squared, equals mc squared. That's Einstein's equation. So you can convert energy into mass and mass into energy. So there's so much energy around a black hole that you can have two particles being formed, typically an electron and a positron.
Yes.
One of that pair goes into the black hole, the other part escapes.
Mm-hmm.
And so we see that radiation coming out from a black hole.
Okay.
So slowly that will evaporate. Energy comes from the black hole and the black hole evaporates.
Okay. So another question is from John. How we can do astronomy from home? What are we can do related to astronomy from home?
Yeah, now there's many ways to do astronomy from home. The easiest way is to look at a site like planethunters.org. Excuse me, do a look at a site like planethunters.org. And what they do is that they have all the tools to look at data from the Kepler satellite. So you can look at data and you can try to use their data to find new planets. That's one way. It's an easy way. If you want to do more detailed work, then there's a little more work involved in that. It's you can download data. As I go to the Hubble Space Telescope and download any of their images. If you want to look at the Eagle Nebula, you can download that data. You photograph, you can't do science from a photograph. You have to look at the actual scientific data. In order to look at the scientific data, you have to use software.
Yes.
Things like FITS software. I use many Python. There's a lot of tools built into Python that you can use to look at astronomical data. One of the simple things that I tell people about is that you know that hot stars they're hotter, so cool stars are cooler, so they look red. So you can look at two pictures. You can look at a blue picture and a yellow picture. And if you blink the two, the hot stars will look blue, the cool stars will look brighter in yellow. So you can pick out stars. These are simple things that you can do. As you get more involved, you learn more, then certainly you can do complicated things. I do have students now who I'm trying to teach to do more complicated things.
Okay, that's good. Great, sir. Another one is from Mohan. He has asked, what are the research works under PhD program currently under astronomy? For PhD.
How do you get into a PhD? Or what was the question?
No. Research works available. What are the research areas available?
What are the research areas available?
Yes.
No, that's research goes through the whole area of astronomy. Mm-hmm. So how you decide what field you're into depends on the university, because astronomy itself is so broad. People work on the sun. You could have people work on planets, on extrasolar planets, on quasar galaxies, interstellar medium like I do. And so it depends on the university. And you look at people available at university and you find out what topics they work on. And so the problems available to a PhD student are basically the problems available with the professors at that university. So if you want to work in some particular area, you know you've made up your mind, I only want to work on extrasolar Jupiters, then you should find a PhD program where they have scientists who work on hot Jupiters.
Yes. Yes. So another one from is asking that what is the difference between cosmology?
Between astronomy and cosmology, cosmology is a part of astronomy. Cosmology deals specifically with the distant universe. And so you look at faraway objects, look at the early universe. Faraway objects means early universe. So you look at early universe, how the universe started, the large-scale properties of the universe. So it's a part of astronomy. Because as I said, astronomy is huge. Astronomy is anything. Any sky is astronomy.
Another one question is how to access the data for astrophotography. Astrophotography.
Astrophotography, very often what you do, again, let me go into two things. One is that a lot of the astrophotography that you do now, they do deal with FITS images. The data you get from commercial CCDs, if you go out and you buy a telescope, the data will come as a FITS image. That you can do with Photoshop even, or MATLAB. So you can access that. If you want to access data from astronomy, from astronomical spacecraft, you can do that through their JPEG files at whatever resolution you want. Files, 8,000 by 8,000 pixels. Or you can get their FITS images. And then you can scale that, you can make that look however you want. If you get a JPEG file, there's not much that you can do. They've already processed it. If you get a FITS file, now you can process it yourself. Maybe you want to bring out the faint regions. So that you can do from the FITS file. And FITS files you can do in Photoshop. Photoshop will let you do it. MATLAB will do it. GIMP will do it. So there's any commercial ways to do this.
Another one question from Pratik. How will string theory contribute to astronomy?
Yeah, no, string theory is one of those funny things. They anytime you find out something wrong in string theory, they change the theory on you. So string theory is it came out about because of these extra dimensions, and certainly there's a lot of predictions that they may make, but as far as I know, there has been nothing observable to date. So we've got nothing, no evidence that there actually are strings out there. So that way I can't say that it's contributed to astronomy in any significant way.
Yes, sir.
Of course, all the string theory people will come out and they'll write nasty comments here.
No issue. Another one question from Monica. Wormhole is there or not, sir?
A wormhole is, there's one of these, when you only play with equations, and this applies to string theory also, when you only play with equations, you come out with lots of things, lots of predictions. You know, we have to deal with things that we can observe. And so far, no one has showed how to observe a wormhole. And so no one has observed a wormhole, and no one has shown how a wormhole would affect anything that we see. So let's say that a wormhole is something interesting. Like strings, it's something interesting that's out there. But so far, to show that it exists. Maybe in the future, we'll come out with real predictions, and then we can say something. Right now, there's nothing I can say.
Subhasubramanian sir, is there any question from your end?
Sir, one question from the audience. Can entropic force explain dark energy properly? Sir?
Well, the reason we call it dark energy is because it's dark. Dark meaning we don't know much about it. And there are different ideas of explanation. There are different ways people explain it. But again, I don't think there's anything very convincing. Not speak too much about it. It's a very humbling thing. We don't really know what dark matter is. We don't really know what dark energy is. So we don't know what 95% of the universe is.
Okay, sir.
Mm-hmm.
So another question: in which condition circular orbit motion of a satellite changes to vehicle?
You have to have some propulsion. I mean, the orbit will always be elliptical to some extent, right? Because you can never get a perfectly circular orbit. But in order to change orbits, you have to use some propulsion. So this is the way they put satellites up. They very often they put it up into one kind of orbit. They let it go, and then they change the orbit by applying some thrust. They light their rockets at some point, and they push it up to another orbit. Always you do it through rockets, through rocket propulsion. Unless you collide with something, of course. If you something, or you maybe you're changed because of the gravitational influence of something. So Jupiter, for instance, many of the collisions that we have now are because they came too close to Jupiter. They were in a stable orbit, then they come too close to Jupiter, and Jupiter changes the orbit so that their orbit is they change from one elliptical orbit to another.
Okay, sir. Sir, there are so many questions floating in the chat box. So as we don't have that much time, so I will compile every questions and I will send to you, sir. So when you are having time, you can give reply to those questions.
Sure, you let me know. As I've said, I'm always happy to arrange a special session with some of your students. Okay, if they want to just to ask questions.
Yes, sir. Sure, sir. Sure. We can arrange in a fine day. And final question from my side: what are the available for our students to work with the Indian Institute of Astrophysics?
Yeah. So let me broaden that and say, what are the opportunities for students to work with any scientist? Mm-hmm. And so there are many scientists, of course, and some people are busier than others. Some people are like all people. Some people are better at questions. Some people don't like answering questions. So what I would suggest to your students is that if you're interested in doing anything in science, to write to people. But before you write to people, don't write to 100 people. I reply to every message except that those where I'm one of 100 people in the email, to XXX, to YYY, and so on.
Yes,
those
yes,
I figure no point. So write to people. Don't write a generic email. Okay. Don't just write, I am this, I have so much, I have done this. Rather, make it a little personal. Look up what the person does. Okay. Make sure that you're interested in what they do. Okay. For instance, I don't work on cosmology. So if I get someone who writes to me and say that they want to work on cosmology, yes, I just tell them I don't work on cosmology. Yeah. So do that, and then don't be discouraged. Many people may not respond. Many people may respond. Many people may say, no, I don't have time now. Okay. But make it personal. Try to connect them and tell them this. I'm very interested in doing this, and this is the kind of stuff I would like to do. Okay. And if they do that, then I'm sure that they will reach they will get a positive response one way or another.
Yes.
Of course, now we have this problem that we're not taking interns in person. No one is coming to IAA, but I am supervising several students remotely.
Okay. Sure.
And many people are doing.
Yes,
Many
sir.
people
I will
are.
let our students know of that, and we will contact you on the time. Thank you,
I
sir.
don't all be right
No,
to other
no,
people.
no. Yes, sir. Yes, sir. Of course,
Okay.
we will segregate and we will do that. No issues. Thank you, sir. And first of all, I would like to thank Niti Aayog, Atal Innovation Mission from Government of India, whom we have done this, especially the wonderful event of the day, Space Astronomy by Jayant Murthy. And I would like to thank Atal Incubation of Kendra Vidyalaya, Chandigarh, Kendra Vidyalaya Air Force, Chandigarh, with help of a principal as well as vice principal, as well as the incubation center manager. So without their help, this event is not going to be a successful one. And I would like to thank the participants, those who have registered for this event and those who have watched live. More than 1,000 people have watched live in this session. So it is a great thing. And right now I will be sharing the procedure for certificate, how the participants can download the certificate. And finally, I would like to thank you, sir, once again for accepting our request. And it is a great day, and wish you all the best for your future.
Thank you for arranging this.
Yes, sir. Sure. So I'm going to present the procedures.
घर पे क्या होता है देखो ठीक है वहां जाऊंगा फूड टिकट करना पड़ता है फिर नोटिस यहाँ आऊंगा विल टेक टाइम वेस्ट होगा मुझे उसमें
I can leave now? Or?
Yes, sir. You can leave, sir. Thank you. Thank you, sir.
हाँ घर पे पहुंच वहाँ 24 घंटे बैठ के तैयार हो अलग से उसका
Dear participants, kindly log into academy.wingsofarrow.in. We have already shared you the procedure of downloading the certificates. Hope you might have seen the procedure. If anyone is missing that, I request you all to register first of all. Those who are not registered, you register through academy.wingsofarrow.in. So once you click the new account, a registration box will be opening for new account. So where you can give your email ID and you can generate your password also. So once you registered, you can enter into the module. And particular space astronomy is under category. If you physics category, you will get the space astronomy of today lecture. So access to that and enroll yourself. Option called enroll. Once you have enrolled successfully, there will be a feedback form. Form will be there. So in feedback form, after giving the feedback, the certificate will be automatically generated. Okay. So you to give the valuable feedback and suggestions to our platform, how we can improve and what you are expecting from us in the next event. Okay. So what type of topic you need, you can suggest over to us. So with this, I conclude the session, and once again I will thank the participants and as well as the arrangements done by Kendra Vidyalaya Higher Secondary School from Chandigarh. Thank you. See, one more thing I want to insist that the link academy.wingsofarrow may not be opening. It will be available for 5 days, since due to the server error, where more than 1,000 participants are entering into the particular platform, the certificate will be available open for 5 days. So anytime you can download with the same procedure. Already we have mailed the step-by-step procedure in your mail ID. Kindly go through your mail. So once if you have any queries, you can talk to us through contact at. Thank you. With this, we are ending this